All right, welcome to the Homework Solutions for section 5.2. We are on page 327. Going to work 1 through 13 odd, 19 through 25 odd, and number 63. I was able to get the first four on the board here. So if we're integrating 1 over x plus 1 dx. So if we let u be x plus 1, then the derivative of that is just going to be 1. So du is equal to dx. So we can write this in terms of u as 1 over u du. And the antiderivative of 1 over u would just be the natural log, the absolute value of u plus c, and then we're going to have to plug back in our u in terms of x. And so that one, of course, is a pretty simple one, and you could check that probably with your eyeballs and see that if you take the derivative of that, you're going to be right back here. All right, for number 3, we're going to let u be 3 minus 2x. So the derivative of that is negative 2 dx. We need it to just be dx, right? It's 1 times dx or dx. So if we multiply both sides by negative 1/2, we'd have negative 1/2 du is equal to dx. We could rewrite this integral with a negative 1/2 out front, and then 1 over u du. So that's going to be negative 1/2 times the natural log of the absolute value of u plus c. Negative 1/2, we're plugging u back in, natural log of 3 minus 2x plus c. If you take the derivative of that, you're going to end up with 1 over 3 minus 2x times negative 2. That'd cancel out the negative 1/2, and you'd be right back here. All right, number 5, we have x over x squared plus 1. So if we let u be x squared plus 1, du is 2x dx. Half of du would be x dx. We can rewrite it in terms of u 1/2. And then we would have du, that's x dx is du over u. And that's the natural log of the absolute value of u plus c. Then we'd have 1/2 times the natural log of x squared plus 1 plus c. Okay, number 7. So probably the way I would do this is rewrite it. The x will go into x squared x times, and then minus 4 over x dx. Now 4 over x is going to be a natural log antiderivative, but x we could just use the power rule for integration. So that'd be 1/2 x squared minus, really don't need to do a u substitution here. It's 4 times 1 over x, so 4 times the natural log of the absolute value of x plus c. All right, that does it for the first 4. Okay, number 9. So we're going to have x squared plus 2x plus 3 on top. And on bottom, x cubed plus 3x squared plus 9x. So you want to pick a u so that it's just sitting out in the problem if you take the derivative. So let's let u be x cubed plus 3x squared plus 9. And then du is going to be 3x squared plus 6x dx. Excuse me, plus 9x, so plus 9 dx. I need it to just be a third of that, right? So 1/3 du would be x squared plus 2x plus 3 dx. Funny how that works out. So we can rewrite this in terms of u. I have a 1/3 out front. Du is just this, so that's du on the top, u on the bottom, because we let u be the denominator. So that's 1/3 times the natural log of the absolute value of u plus c. And that's 1/3 times the natural log of the absolute value of x cubed plus 3x squared plus 9x plus c. All right. If you took you could check by taking the derivative and then When you do that, the 1/3 will be canceled out by the 3 that you would have on top, and you would get back to this original equation here. All right, let's do number 11. So 11 is a little more interesting. Natural log of x all squared over x dx. So here, if you let u be the natural log of x, so usually we're letting, a lot of these we let u be the denominator. It doesn't always work. If we let u be the natural log of x, then du is 1 over x dx. And you can see 1 over x, or dx over x, is sitting right there in the problem. Okay, so we can just rewrite this as u squared du. That's going to be 1/3 u cubed plus c. So that's 1/3 times the natural log of x all cubed plus c. All right, so there you go. Could we check that? See if we get back to here. So that would end up being, if we wanted to check it, I think this one's worth checking. So to take the derivative of that, you'd bring the 3 times the 1/3. That would cancel, so it's the natural log of x squared times the derivative of the inner function, which is 1 over x. So you end up with the natural log of x all squared over x, which is exactly what you need here. So some of them definitely, I think, some of them you can check with your eyeballs. Some of them you need to maybe write it out on paper just to see if you got everything right. Okay, number 13. So we have 1 over the square root of x plus 1 dx. Now, one of the reasons I assigned this was because you're used to everything being du over u in natural log, but that's not what this is. All right, this is right back to chapter 4. If we let u be x plus 1, then du is just going to be dx. We can rewrite this integral as du, because that's all you have on top is dx, over the square root of u, which would be the same as u to the minus 1/2 du. That's going to be add 1, that's u to the 1/2, but we need a 2 out front, plus c, so that's inserting u back in and putting it in a radical form. It would be x plus 1 plus c. So there's no natural log involved at all here, and if you want to check that by taking the derivative, it will work and get you back to 1 over the square root of x plus 1. All right, let's take a look at 19. So now we're getting into the trig. We have cosine theta over sine theta d theta. Now, you might recognize that, hey, that's cotangent, and I have a direct formula for that. You could do it that way. I'm going to go ahead, though, and do the u substitution. But you could rewrite this as, hey, that's cotangent theta, and then plug the form. Oops, sorry about that. That's cotangent theta d theta, and then go straight to the formula, right, which be the natural log of sine theta, absolute value of sine theta plus c. But I'm not going to do it that way. I'm going to go ahead and do the u substitution. So if we let u be sine theta, du is cosine theta d theta. So we could rewrite this as du over u, which is going to be the natural log of the absolute value of u plus c, and that's the natural log of the absolute value of sine theta plus c. So now we've proved 2 of those 4 new formulas. The first one I did in the notes, and now here's the other one. Okay, that's number 19. We'll move on to 21. Okay, 21, cosecant 2x. Okay, we can't plug straight into the formula because it's not x, it's 2x. So u is equal to 2x. du then would be 2 dx. I need it to just be dx, so 1/2 du is dx. You have a 1/2 out front, cosecant u du. All right, so let's look at your formulas. That's 1/2. You'll end up having this 1/2 comes down times minus the natural log of cosecant u plus cotangent u plus c. And then we've got to plug u back in. So that's minus 1/2 natural log of the absolute value of cosecant 2x plus cotangent 2x plus c. All right, but you do have to go through the u substitution there and show that to me. So don't just go straight to the formula. 23. All right, we have cosine t over 1 plus sine t dt. Okay, so we can't go straight to the formula here. Let's try a u substitution. Let's let u be 1 plus sine t. And then du is just cosine t, right? The derivative of 1 is 0, and then sine is cosine dt. That's all. I've got that on top. So now I have du over u, which would be the natural log of the absolute value of u plus c. So that's the natural log of the absolute value of 1 plus sine t plus c. And I can kind of take the derivative with my eyeball there and see I'd go right back up to the original equation. It would be 1 over 1 plus sine t times the derivative of 1 plus sine t, which is cosine t. Okay, let's see if I can fit 25 on the board here. Maybe making a mistake. Let's say we've got secant x tangent x over secant x minus 1 dx. Okay, I see that if we let u be secant x minus 1. The derivative of secant is secant tangent, right? So the derivative would be secant x tangent x dx. Okay, so that's going to be just du over u. So we don't even have to adjust with some sort of fraction or coefficient. It's just du over u. Well, that's going to be the natural log of the absolute value of u plus c. Natural log of the absolute value of secant x minus 1 plus c. So if I take the derivative of that, it's going to be 1 over secant x minus 1 times the derivative of secant x minus 1, which is secant x tangent x. So that works. Brilliant. All right, we got one more to go. All right, number 63. So 63 says the demand equation for a product is P is equal to 90,000 over 400 plus 3x. We want to find the average price between 40 and 50. Okay, so to find that average price, we're going to have to, between 40 and 50, we're going to have to do 1 over 50 minus 40. We're going to integrate from 40 to 50 of this function, 90,000 over 400 plus 3x dx. So this is just 1/10, right? I can bring that 90,000 out front. So if I bring it out front times 1/10, it's going to be 9,000. And we're going to integrate from 40 to 50. Again, I'm bringing that 90,000, but I'm multiplying it by 1/10. So that's 9,000 of just 1/400 plus 3x dx. Okay, let's let u be 400 plus 3x. And then du is just going to be 3 dx. I need it to just be dx. So 1/3 du is dx. So we can rewrite this as 9,000 times 1/3, bringing that 1/3 out front here, 40 to 50. In terms of u, we're going to have just du over u. Well, 1/3 of 9,000 would be 3,000, right? So 3,000 times the natural log of the absolute value of u evaluated from 40 to 50. So that's 3,000 times the natural log of 400, absolute value of 400, plus 3x, plugging back in for u, evaluated from 40 to 50. So that's 3,000 times the natural log of 400 plus 150, right? If you plug in a 50 there, so that would be 550 minus 3,000 times the natural log. Let's plug in 40. That'd be 400 plus 120. So 520. So that's just a matter of sticking that in your calculator. Okay, so what the heck? Let's go ahead and do that. You can do that on screen here. So let's find the natural log here. So we've got 3,000 times the natural log of 550 minus 3,000 times the natural log of 520. That's $168.27. All right, beautiful. So there you go. That does it for this solutions video, and I will talk to you on the next one.